region of 0.4 meters square. A current of 0.2 ampere is passed through the coil that gives rise to a magnetic flux of 1 milliweber. Now that the current we are talking about is a DC current. We haven't started yet in AC concepts, but what we are trying to do is to understand the fundamentals of electromagnetism in order for us to apply these concepts to a transformer more effectively and quicker. And the question says, calculate the MMF produced by the electromagnet. So how would you calculate MMF, or magnetomotive force? Since MMF is equals to ampere turns, or Ni, N is the number of turns, I is the current. You got the turns, which is 5,000 turns times 0.2 ampere. This gives you MMF. Part B of the example question says, calculate the magnetic flux density of the core. And that is B is equals to phi over area. So since you have got the area in meter square, you don't need to convert. You just need to use the same. And you got the flux, which is 1 milliweber. So 1 into 10 to the power minus 3 Weber divided by cross-sectional area, which is 0.4 meters square. This gives you the magnetic flux density. And finally, the reluctance of the magnetic circuit. Now, there are two methods to calculate the reluctance of the magnetic circuit, and one is F is equal, or MMF is equals to phi times S. Another formula is S is equals to L over mu times A. You don't have the length of the core, you don't have the relative permeability of the core, so it would be more convenient to use MMF is equals to phi times S, because you do have MMF, you do have phi. And that's the solution, and as you already have the solution of this, but for me to make sure that we understand the basic concepts. Magnetizing force or magnetic field strength. We represent this magnetic field strength with the letter H. And what it means? Well, magnetizing force in a material is defined to be the magnetomotive force per unit length of the material. The unit of the magnetizing force is ampere turns per meter. So when MMF increases, the flux increases. Also, the magnetizing force increases. In other words, the magnetic flux density is directly proportional to the magnetizing force, H. Now, this is a simple example question. If we have the fixed number of turns on a piece of core of a material, let's say 1,000 number of turns of a coil wound on a piece of material, and both materials have a different length. The one material has 100 millimeter and the material has 400 millimeter. Now we want to calculate how much magnetizing force or magnetic field strength it would have if we change the length of a material. So by applying this ampere turns per meter, and it is evident that coil 1 achieves higher magnetic field strength compared to coil 2. That means if you have the shorter length of a material with the same number of turns, it will produce the stronger magnetic field strength or magnetizing force. That's why the length of the material plays a significant part in constructing the transformer. Now we are again going back and forth to the permeability concept. Well, of course, we know that the permeability is how easy it is for a material to establish the magnetic field if you supply a DC current, and how easy it is for the same material when you switch off the DC current. That means the material should ideally not be storing any magnetism. So the best material for a transformer is the material, when you apply the magnetism, it should not store any magnetic domains within the molecules of a material. And that's not possible. You can reduce it by improving the material's permeability, but you can't say it has zero or higher or infinite permeability. It's more like a porousness of a material, how much it can absorb. There are three types of permeability. One is absolute permeability, second is relative permeability, and the third is permeability of free space. So it was calculated in the free space, in the vacuum, and the value was calculated as 4 pi into 10 to the power minus 7 Henry per meter. It's more like a permittivity in the electric circuits or in electrostatics or in the capacitive concepts, which is 8.85 into 10 to the power minus 12 farad per meter. So permeability of free space is constant, and we always have a relative permeability. So the relative permeability does not have any unit because it depends on the material and it depends on the ratio between absolute permeability and the permeability of the free space, which we will look at the formula later on. So it is always important to have a higher permeable material. Higher the permeability, lesser the losses. It's a simple possible connection because it will store the less possible magnetic domains. And those, why? Because the magnetic domains actually react with the supply current and creates the harmonics, which is a distortion to the supply frequency. Now, of course, these concepts will be more clear when we start the transformer section. But I just want to clarify that these are the terminologies, the word necessary for us to understand the construction operation of a single phase transformer. So absolute permeability is equals to the permeability of free space times the relative permeability. The absolute permeability is the ratio of magnetic flux density to the magnetic field strength. Sometimes we can represent it in terms of BH curve, which is the hysteresis loop that determines the performance of a machine. Any machine, motors, generators, transformers, you name it. Anything that uses the coils would have these problems, and you can explain these problems by knowing the terminologies of the magnetic circuits. Now we have another example question. A cast iron former of mean length of 0.28 meters has a cross-sectional area of 150 millimeters square. 150 millimeters square into meter square, that would be 150 into 10 to the power minus 6 meter square, and is bound with a coil of 400 turns. The coil carries a current of 3 ampere DC and gives rise to a flux of 0.2 milliweber. Calculate the MMF produced by the coil, magnetic field strength, magnetic flux density in the core, absolute permeability, relative permeability, and the reluctance. And here we already went through the solution of this example question. I would try to save the time, but it's basically based on the concepts that we just went through. So if you have the concept, you know the formula, and you can apply to that example question. I have already clarified these things in the class, that the concept of electromagnetism, the reluctance, permeability, MMF, magnetic flux density, magnetizing force are all important to understand the transformer. So you will probably not find very much, specific in depth in this electromagnetic concept that requires more time to go into details. But of course, just want to understand the basic fundamentals of the electromagnetism. That's what it was all about. I mentioned about the reluctance a little earlier, that the reluctance can be defined as the opposition to the establishment of the magnetic field, and of course we have the formula MMF is equals to phi times S. Here S is represented for reluctance. I just want to clarify S in AC concepts can also be represented as apparent power. So please do not confuse with the reluctance S variable symbol here and with the apparent power symbol, which we've been mostly involved in the RLC AC circuits. So here if we can substitute the equations for magnetic flux density, as you can see B is equal to phi over A, and the equations for mu, which is B over H, if we substitute that equation, then we can derive the formula for the reluctance. Since H is equals to ampere turns per meter and B is equals to phi over A, absolute permeability mu is equals to mu naught times mu R. So that's how we substitute the equations, and we can derive the further equation for the reluctance in a magnetic circuit, which is L over cross-sectional area times mu naught times mu R. Example of the reluctance, then we have the length, cross-sectional area, relative permeability. So let's read that example question. A magnetizing force of 5,000 ampere turns per meter reduces the flux density of 0.5 Tesla in a ferromagnetic core of mean length 0.66 meters. The core has a cross-section of 60 by 50 millimeter. Calculate the reluctance of the core. Well, first we have to convert that 60 millimeter by 50 millimeter into meter square, which would be first multiplication of 60 to 50, 3000 millimeter square into 10th power minus 6 would then become a meter square. Since mu is equals to B over H, so we can use mu value in this equation. S is equals to L over mu times A. So, which is basically the simple B over H calculation. And 3000 into 10 power minus 6, which is the conversion of millimeter square to meter square. And in this way, the reluctance value